Our next speaker is Siniasish from SU. He'll be talking about the UV spectra of 03 FG light Taiwan spectrum. That's their comment.
Thank you. So I'm talking about UV spectra of 203 FG light Taiwan supernova. So 203 FG light, or in short we call them 03 FG light, are actually type 1 supernova, but they are peculiar. They have many unique properties, and one of them is that they are UV bright. And we know that type 1 supernova are used in cosmology as standard candles, but we cannot use these supernova in cosmology because of their peculiarities. So I will show you some of the reasons why we think they are peculiar. So this is a busy plot, but I want you to focus here. This is actually a plot between the maximum MB magnitude, absolute magnitude, with the delta 15 of that on supernova, and this is the Phillips relation, a relation between these parameters which are used to correct for the scattering in the absolute magnitude, peak magnitude, which is used for cosmology. So, but my talk will be focused on events here, which are lying here. So these objects do not follow the Phillips relation, but they are type 1 supernovas. So we have to be very careful when we do some cosmological analysis, because we don't want our data to contain this event. So this is very useful. So it's very we need to be very careful about data selection. So here we show that they do not follow the Phillips relation. This is the first kind of peculiarity of this object. So my talk will be focused on 203 FG light, but the first object was discovered in May in 2003. This is the Hubble image, and this is the light curve. So these events have a broader light curve. So they have smaller delta 15, and this is the spectra. The bold is the spectra of the 203 FG, and this one is the spectra of the normal type 1. Just to compare the spectrum. So from the spectral, so this is actually an optical spectra. So it looks kind of similar. In optical they look fairly similar, but in UV things are different. So yeah, so they have broader light curves. This is actually a very interesting figure. The top panel shows the light curve. So the colored points are actually the data for these 03 FG light objects. And the gray points are for the normal type 1. Just to compare their light curves. So the top panel shows the results for optical bands, B and D bands, and the lower panel shows for the radar bands, R and I bands. The defining trait of these objects is that they do not have a secondary maxima in R bands and I bands. The secondary maxima is caused by a recombination of iron group elements. So these objects may not undergo this recombination, or maybe something else is going on in the explosions, and they lack this iron, the secondary maxima. So that does not mean that if you don't see a secondary maxima, it's a 03 light, but it's one of the signatures of these objects. So this is the second peculiarity of these objects. This is another light curve comparison. In the top panel, I show the light curves in the UV bands. These are actually filters from the Swift telescope. So and the lower panel shows the results for the optical bands. So in the UV you can see that. So there are three types of points. The blue is for the 03 FG light, which is the focus of this board. The gray points are for the normal type 1A, and the orange points are actually a different subgroup. They're actually subluminous compared to normal type 1. So we'll not talk about the orange points. We'll focus on the bluer points. In the UV, you can see that they are clearly overluminous compared to normal type 1. But in the optical, they are luminous, but not so significantly brighter compared to normal type 1A. But in the UV, they are overluminous. This is actually a color curve. Top panel shows the results for actually most of the panels show the results where they start from a filter from Swift and another filter from another test or something. So the main thing here is that they are brighter in the earlier epochs. So in the earlier epochs, you see they are brighter, and of course they are also brighter in the later epochs, but it is more brighter than normal Typhoon in the earlier epoch. So they are bluer than most normal Typhoon. So these are the peculiarities of these objects. So this is a plot published by Panatel a few years back. What they show here is that this is actually not, this result is not for 03FG, like it's for normal Typhoon. This is the most important word in this slide, normal Typhoon. So what they did was they grouped the supernova normal Typhoon into two groups based on their host masses. Okay? So if the host mass in log scale is less than 10 or greater than 10, and they just take the mean of all the Typhoons. And then what they found is that if the host mass is lower, then they tend to have a higher UV flux, and vice versa. So the reason I show this slide because I want to test this argument for 03FG light. Okay. And they did the same for metallicity, and they found that if the host metallicity is lower, it leads to enhanced UV flux. Again, the normal Typhoon. The reason I show this is because this is the most important line. 203FG light intersect low-mass galaxies. So just now I showed the slide where we found that the normal Typhoons tend to have higher flux if they are in low-mass galaxies. So the idea here is to test if 03FG light also reside in low-mass galaxies. Can this be the cause for the UV excess? Can this be the cause that they are UV bright? These are the four objects which I'm working on. We only have four objects for which Swift have spectral data, and these are the results from previous studies, and they found that they tend to reside in low-mass galaxies. So the idea here is to test the argument posed by Panatel a few years back that and to see if that argument can be applied to 03FG light. That if the host galaxy is low massive, is less massive, can it explain the UV excess of these kind of objects? Okay, so before I go into results, I used the data from Swift, and the UV observations are taken from UVOT telescope. Here in this, but the problem with this instrument is that it doesn't have a slit. So in addition to the supernova spectra, you get many other contaminations, right? So you need to correct for the background contamination. So there is actually a default pipeline, but it doesn't. It's not very efficient if you have bright sources nearby. So I wrote a pipeline where we robustly clean the spectra from background sources, and the way it works like this. So basically, this plot is basically you're seeing from here. So you're seeing perpendicular to the trace. So what you get here is that you get a Gaussian profile because you see more counts. This is pixels and this is counts. So you see more counts on the pixels where you have the trace. And from there, this is actually an interactive plot where the users can select the aperture sizes. And this is actually a bright source. So if you use the default pipeline to clean the spectra, you will have contamination from this bright source. So what you do here is that you can select as much width of the trace you want, and then you can select the background aperture as well. And then what the code does is that once you have the background apertures, then it just interpolates the flux at the location of the trace, and then you can clean the spectra in this way. And this is actually a reduction of 2020 HPF. It is one of the sample 03FG like object. And you see, this is the clean spectra, and this is the background spectra. It has some features. It could be due to some bright sources nearby. And actually, you can repeat this until you are happy with the results. So we plan to make this software available in the near future, very soon. So we use our pipeline to reduce the spectra of 03FG light. So there are four. This has actually observations at two epochs. So this panel is arranged in ascending order of the phases. So -10, -3, -2, 5.8, 8.1. The colored profile, the colored spectra are the spectra for the 03FG-like object, and I compared the spectra with normal type 1s. So this actually is a different way to look into the UV excess. So before I showed you that they are brighter in UV from photometric point of view. So this is actually a spectroscopic point of view where we can see that they are from spectra. We can also observe that they are UV bright compared to most normal type 1s. No matter which phase you take, it's more brighter. It's brighter than most or all of the normal type 1s. Okay, so before I showed you a slide, Panetel published a model mean spectra. So here, what I did was, I took their spectra, mean spectra, and I tried to compare. So they have two mean spectra, one for the low mass and one for the higher mass. So I took their lower mass, low mass means spectra for the low mass galaxies, and I tried to compare. So let's focus on this plot. So this is actually a plot of HBF. The red is the smooth spectra, and the blue is the result for the normal type 1a. They both have similar masses, mass around 10 or 12. So this object has a mass of force mass of 9.5 in log scale, and mean spectra has mass less than 10. So this is a model which I want to compare. So the idea is this: if the host galaxy mass drives the UV excess of 03FG light, then this spectra should overlap the spectra of 03FG light because they have similar stellar masses, but it does not, and there's a wide gap. So based on the figure, actually from both the figures, it's actually a different object, 2001 to the n, similar 9.8. Similar, we find that in both cases they do not match the observed spectra. So from this we conclude that the UV excess in this object is not related to host properties. Host property in this case is stellar mass. I also repeated the same thing with the metallicity. So this object's metallicity 8.5, and this mean spectra has. So I compared this with the mean spectra for which the metallicity is less than 8.6, and I get the same result. They do not agree. So from this we conclude that UV excess in these objects is not related to host properties. So we cannot extrapolate the argument proposed by Panetel to this kind of objects. It might hold for normal type 1s, but does not hold for these objects. So yeah, that's conclusion. So if the host galaxy does not influence this UV excess, so what does? So we don't answer that in this mode. In this mode, we just focus on what if the host galaxy does influence or doesn't. So it only doesn't. So we think that if the host galaxy is not the factor which drives the UV excess, maybe carbon-rich CSM could be an answer, because there were some papers which claimed that they found some signatures which could indicate that when these events explode, they're exploding in an environment of dense carbon-rich CSM. This carbon-rich could be because there's a two white dwarfs, and the smaller white dwarf is disrupted, and it creates this carbon-rich CSM. And when this supernova explodes, the ejecta interacts with the carbon-rich environment, and it produces additional photons. Smaller than photons, UV X-ray photons, and this could be the answer. This could be one of the ways you can get this more UV excess in these objects. So yeah, I did conclusions and I take questions.
Thank you very much. Maybe one or two quick questions. Sorry, Tomaki.
Thank you for myself. So I want to ask you about mass of CSM. So do you have any idea? How much mass of CSM?
Mass CSM?
Yes.
We did not focus on that. We just think that if there is a two white dwarfs and a smaller white dwarf, 0.6, 0.8, maybe it gets disrupted on the tidal forces and it creates the CSM. but there are no constraints on the mass of the white dwarf, which would lead to this UV excess. Yeah.
Okay. Any more questions? Roger.
Thanks for the question. Sorry that I missed a little bit. Is this UV exists always happen during the event or only in a certain time periods?
Of this inspection, the UV excess, it's always UV bright. It's in any phase. Yeah.
In time, in terms of time.
Yeah, in any phase you see they are UV bright, or in early phases it's more bright. I don't think it's an easy question.
Okay,
Sorry for running out of time. Next speaker again.